watching us.
They have arrived.
After a mission to abduct humans for food gets cut short from a lightning strike malfunction, a group of a few hundred aliens head back to their planet with approximately 2,000 humans on board. The damage being more severe than initially thought, the alien ship is forced to crash land on a moon orbiting a distant planet. Approximately 100 aliens and 1,000 humans escaped the crash. The humans notice the aliens running for cover from the sun as it burns their skin, a benefit humans have in the race for survival. But the humans know that once night falls, the aliens will hunt their only source of food for survival. And with that knowledge, the humans regroup and decide to use math to find the fate of humanity. Okay, here are the assumptions for the predator-prey equations. In the absence of aliens, the human population will change over time exponentially, that it is equal to or proportional to the size of the population. So we'll see an exponential growth curve in the absence of aliens. However, in the absence of humans, the aliens will not have a food source, and therefore they will decay over time proportionally in a negative way. The effect that the two populations have on each other, well, it'll have a negative effect on the rate of change for the humans because the aliens will be hunting the humans, and it'll have a positive effect on the aliens as the aliens will be eating a food source. Now, the effect of interactions or encounters will be proportional to the product of the two populations, A times H. So in each differential equation, we can represent the effect of the two populations as a proportional constant times A times H, where both of those proportional constants are positive. Now, looking at the system of these two differential equations, we can analyze this system using a phase portrait or a phase plane picture of the predator-prey equations, or otherwise known as the Lotka-Volterra equations. To make things more ideal, we're going to assume all the proportionality constants are equal to 1. So dH dt, or the rate of change for humans over time, can be simply written as h multiplied by 1 minus a, and the rate of change for aliens as a times h minus 1. Now, to compare the rate of change of aliens with respect to the rate of change of humans to find out how the two populations interact, we use the chain rule for derivatives to create dA dH, the rate of change of aliens with respect to humans. And we get an equation that represents a slope, or at every single point in a plane, a slope field. And that plane is known as the phase plane, or the HA plane. Now, when we look at the slope field, we can see some definite flow patterns, and we see that there are 2 points on the graph for which the slope field is undefined, for which there is no slope. Those 2 points would be at 0, 0, the origin, and at the point HA equals 1, 1. To say that the slope is undefined is to say that both dA dt and dH dt are 0, giving us 0 divided by 0, an undefined quantity. And this happens at only 2 points in our slope field. When this happens, we get what we are calling equilibrium points, points at which the two populations do not change or remain constant. Now, if you draw a line that is the line A equals H, or otherwise known as a line of symmetry, you'll notice that the slope field is in fact symmetric about this line. And that is to say, if we were to interchange the variables A and H in our differential equation here, it would not make any change whatsoever. So the equation is symmetric with A and H. Therefore, the trajectory or orbit will also be symmetric about this line. Now, how do we know how the trajectories will be traversed? Well, approximating this numerically, let's pick a point in the plane such as 2, 1. We plot that point and find out what the differential equations will tell us that point will do. Which direction will that point travel along the slope field? So looking at dA dt, how the alien population will change over time at this particular population, we see that we get a 1. And for dH dt, we get 0 at this particular point. So that tells us that the alien population will increase at this point, and the human population will remain constant at that point in time. So according to our graph, the slope field will move the point upward. And the field suggests that it will be traversed in a counterclockwise manner. So let's see what happens at another test point. Let's consider plotting now the point HA is equal to, let's go with 1/2, 1. So now we're going to evaluate both of the differential equations with respect to time at this particular coordinate for these populations. And dA dt gives us a negative 1/2 value. dH dt gives us a value of 1/4, a positive value. So that means that A is decreasing and H is increasing. The point will move downward and to the right. So this indicates the flow of the trajectory, a counterclockwise flow, that the point or the populations will evolve over time along a trajectory that fits into a particular orbit around the equilibrium point. Now, the equilibrium point, again, is where both populations have a rate of change of 0. That is to say that the populations will remain constant. And we notice that our population, HA of 1,1, that is 1,000 humans, 100 aliens, will constitute an equilibrium point at which the populations should remain constant. Now, to kind of get a picture of how both of these populations will change over time, plotted against time, we notice that the trajectory that we found in the phase plane is a closed loop orbit. And this is going to lend itself to some periodicity, a periodic behavior. So here plotted in pink are the humans, here plotted in yellow are the aliens. And we see that they both have a cyclic pattern to their populations. At some point their population is decreasing, at some point their populations are increasing, and they do this in a very periodic or cyclic way. They repeat their patterns over and over again, so we can break those patterns up into pieces or intervals. So the closed loop trajectories mean that the populations will oscillate periodically over time. Unless, of course, you're at the equilibrium point at which the populations will not change at all. Both populations have the same period. The one thing that you notice is that these two populations are just slightly out of phase, hence the phase plane. The humans reach their peak about a quarter cycle before the aliens do. That is, that they are at a maximum population before the aliens will reach their maximum population. Let's summarize what we talked about today. So the aliens and humans in populations of hundreds and thousands respectively, we set up a set of differential equations, a system of differential equations, making some assumptions. And then we looked at what the coefficients or the proportionality constants were, and we assumed them to be 1 to make our ideal case. We then plotted the slope field and found the equilibrium points suggested by the slope field. We noticed that the population series oscillated periodically because of the nature of the slope field having closed loop trajectories around the equilibrium points, and that the equations, or the closed loop trajectories, would be symmetric about the line a equals h, or in graph terms y equals x. Plotting a point in this space will allow you to analyze how the different populations will increase and decrease over time, but all of them will follow some sort of periodic nature unless they live at the equilibrium points. Hey, thanks for watching. I hope you enjoyed this episode. Please like and subscribe and hit that notification bell for more videos. Stay tuned.